got this in here. So this is the equation for there. But let me show you guys some stuff, and punching all the right buttons now.
Was there numbers missing on that one or something?
No, something, the copy of the test that they sent me back from a picture from their phone, the equation was totally gone. It said the equation is here, and there was nothing there on their particular one, which tells me it's an add-in in Microsoft Word that was causing the problem because I used the formula maker to use this. And I'll show you guys that, by the way, so that you guys know where that is, because this is kind of one of those, let's learn life lessons, it's not always about physics, sometimes it's about life lessons.
But if you saw it and it
If you saw it, you should have had it, it should be fine.
Okay.
Yeah, it's just if you didn't see it at all, that's the equation.
Okay.
Yeah, so here's some life fun things. If you go to the NFC webpage and you click on IT resources, you'll go back here, the information technology, and you get the IT resources. Go back. If you go to the information technology page, software and technology discounts. You click on that, and this is how you can get Microsoft Office for your computers. And when you click on that page, it's free with a student ID. You have to use your student ID. So if you didn't know that was available to you, that really is a good thing. Also in here, if you hadn't seen it, these free developer and application software, there's a bunch of things that are in there. And if you go through this, there is a bunch of stuff that is available in terms of computers and tablets, CAD drawing stuff, design, graphics and design, web publishing things, desktop publishing, that you can get at a significant discount or sometimes free. And as I pointed out on Wednesday, there are apps that are totally free as well if you're a student and you use the student ID that you can get the next level. Like the CAM scanner that I showed you, there's a basic level that's free. There's a basic office lens that's free. But if you use your NOC email address, you can sometimes get the next tier of services for it. So that's something to keep in mind. And now I'm going to show you how you can actually use Word to create an equation, because it's a handy thing to have, particularly for science majors. So if we do any kind of just a blank document here, and we're typing in, and we've got this lovely, and I want to use a Greek symbol, or I want to create an equation. If I go here and on the insert bar, you've got an equation tool and a symbol tool. And so your equation tool, if you click on that, you can get x is equal to, and then you can type in fractions, and it gives you your fractions. So now you can put stuff at the top, and you can put stuff at the bottom. You can do superscripts and subscripts. So if you're doing chemistry type things, this is handy. This is totally handy. And for those of you who may be going on to do biology type stuff and you're writing everything in amino acid sequences, which I read my son's master's degree document, and I swear he wrote a whole sentence in the amino acid protein type whatever documentation it is. It was like, oh, I don't even know this stuff, but those are very, very helpful things that you have. And it gives you all your mathematical symbols, your degrees Fahrenheit, your degrees C, gives you arrows, especially if you're trying to do chains, like if you're trying to do a Krebs cycle, or you're trying to do a photosynthesis cycle, you can use the arrows. It gives you all of that stuff in Word. So it's really helpful for that. And if you've got a tablet, you can do an ink equation, doing your own handwriting. Or if you've got a touch screen, like my particular laptop is a touch screen, I can use my pen and actually put it in there as well. So that's something to know about. And your symbols, they have tons of different symbols. Everything from your special characters, currency symbols, Greek letters, super simple subscript. If you want to do phonetics, for some of you that have to do phonetics, it's got that in it as well. But it's something that people don't necessarily show you. Even in your, if you took the computer science class that's supposed to help you look at what's in Word, this is not stuff that they're going to show you because it's not the common stuff that everybody else is going to use. It's stuff that we as science majors and stuff use a lot. Totally use a lot. And in fact, when I first did, when I was way back when, I had to actually buy a separate piece of software to write equations. So the fact that it's now in Word is like super, super nice. Super nice. So if you didn't know that this was available to you, this is available. Okay, I think you guys have probably heard it in many of your other classes about when you join in online, there's a lot of people that want you to have your video cameras on. I am not that persnickety about it, as you guys have noticed, because I haven't said anything about it up until this point. I am cognizant of bandwidth issues. I'm cognizant if you're trying to do it through your phone. Some of you are using up phone data in order to do it. As long as you are responding to me in the chat, and I know you just haven't disappeared off the face of the planet, I am not going to be that persnickety about having your video on Zoom. But I do want you guys to respond, all right? And so far, it's been okay. I mean, you guys out there, if I have the chat up, I'm actually seeing stuff going on in chat, and I appreciate that. And that's made me not so worried about folks not turning on their video. And especially if I were to do, like, share my screen from my laptop right now, I'm going to do that. See, we're going to give it a whirl. We're going to give it a try this morning. So if I share this screen, and I'm actually sharing the screen, and in some cases, people, if I want to go ahead and have it out here, I'm going to move this over here. And I'm going to actually bring this up so everybody can see everybody on the screen here. It's interesting. Stop share. Want a new share. Stop share. I want my new share. Okay, I want to do that. Maybe just hit. I'm not getting everything that I want. Oh, because I'm sharing from the other screen. That's what's happening. This is one of those cases where sharing from one side to the other is kind of different. But it can also be distracting. If you're in a different kind of room than these rooms, it can be distracting. So, again, as long as you guys are doing stuff. Okay, I've got a person that has, what does the I stand for? What I? See what that one is. Okay, so that kind of gets us where we're going. So now I'm going to go over here, back to Blackboard. And we are getting ready to start Newton's laws. Okay, one more thing before I get to that. Please, folks, don't leave the easy 10 points on the table. Fill out your weekly evaluations. Very helpful. And as you guys saw last week, it was what ended up with solutions getting posted on there. So I do read them. I do read them, I read what's going on, and and I will tell you one of the comments in my other class about the test, because I did the same thing in the other class, and I had the test on the 2 pages, and they said, well, they really wanted space on the test to do the work on the test. And I thought to myself, okay, I could do that, but then then everybody else is printing out 10 pages because I've left you space. This way you have as much space as you want to work the problem. So I'm not making that change unless it's overwhelming, but I think everybody would like to have their normal space, as much space as they want to work the problem, versus trying to squeeze it into something really small. So that's one thing. But the other is that when you guys ask for a certain problem, I actually provided you guys the solution and posted it. So there were solutions posted. But one of the things I want to point out for next week is today we're going to actually start Newton's laws, and which means that you folks on chat better get ready because I'm going to ask questions and I expect participation today. I have some solutions and example videos. I really like this guy. He does the Veritasium. He's out of Australia, and he does some really cool things associated with physics and chemistry and a variety of different ones. And it's really nice and fun to see the concepts and how he presents the concepts. So as we come across things where he's done different pieces, I'm going to plug them in. And so I've added a couple of those videos. So while you're needing a kind of a study break or something and you want to make it a useful study break, these are great videos to look at. And if I go back one, I've even put in, I haven't put it in yet, there'll be a couple more that I'm adding in because he does one on drawing force diagrams and what forces are acting on you right now, which is really, really great, especially for what we're fixing to do. And as you all know, I'm always fixing to do something. So I will be adding those videos. You'll see some more of those pop in over the weekend. And the other thing that I did add, and I thought I added one last week, I'll go back and look, because I start to do this, as we now move into a couple of other things that are happening. Let's see if I added them. I start to bring in some Hewitt-Druitt concept videos. And he does a conceptual physics book. And so he does really good screencasts. And he draws much better than I do, as you guys have all seen my artistic ability, which is lacking. But I start posting some of those to help with, well, let's just get the concept down, basic concept. And I will start adding some of those as well. And then every now and then I'll throw in an organic tutor one. Let me answer this question. I get the organictutor.com, he's another good set of videos. So you'll start to see more of those videos get posted. All right, so let's start with forces. Okay, as you guys have probably figured out, physicists are geeks. They're totally geeks. You know, we have license to do a lot of different things because we're physicists. It's really nice. You know, if I were to show up in here, totally mismatched clothes, especially on the first day, you know, before you guys really knew me and you knew I was the physics professor, nobody would question. It's really kind of freeing in that respect because nobody would question. It's a physics professor, we're just all okay, you know, just totally okay with that. But, you know, physics professors are really kind of unique individuals. And I have 6 grandchildren, all under the age of 6. And so as a strange grandparent, I send them books, which is totally good because they love books. But there's a series of books that I love, and it's physics for babies. And my granddaughter loves them. And so she has Newton's laws for babies. She has statistical mechanics for babies. She has thermodynamics for babies, and I love them. They're absolutely, totally fun. So, if my grandchild, who's less than 2, can understand that, we all can understand it, right? It's something that's totally easy to understand. So now, putting numbers to it is a whole different thing, okay? Putting numbers to it, figuring out the equations for it, that's a whole different thing. But conceptually, we can get the idea. So, I have a box. We've just got a box. And my box is sitting on the floor. And there's some things we know about the box. A, it's a box. But what else do we know about the box?
It's one-dimensional.
Well, I've drawn it as one-dimensional. But it's a box, so it's three-dimensional.
Right.
We got gravity's working on it. Yeah, so we got gravity working on it. So we have something that we know we got an acceleration due to gravity that's working on it. What else do we know about the box?
The floor is pushing back as well.
Oh, got somebody that said the floor is pushing back on it. Yay! So we got the floor pushing back on it. So I'm going to represent that. And I'm going to, right now, I'm going to say it's the push from the floor. Okay? Push from the floor. Do I have anybody from chat that's telling me what's on the box? Something else we know about the box. What's the visual image in your head about the box? Okay. Oh, it's showing my laptop screen. Okay, I'm going to stop share. Okay, what do you see now? Okay, so they're seeing the box now. So in your head, what do you see when I tell you there's a box on the floor? What do you see? Hopefully you see a box, right? You got a box. So we know something about the box. Takes up space, doesn't it? And if it takes up space, we can assume something else about the box.
Oh, it has a mass.
It has mass. Now, we don't know how much mass it has yet, but it's got volume, and we know it has mass. So it's got volume and it's got mass. Now, if I want to test how much mass it is, what am I going to do? We got a box. We're going to use the Kleenex box. And we're going to make the assumption that the Kleenex box here has, that we don't see how much Kleenex is in there. This Kleenex box is kind of on the empty side at the moment. But normally, we don't know if the box is closed, or we have a box out there, or somebody's left a package on our doorstep. We know it's got mass to it. What am I going to do to determine how much mass it is? What am I going to do? Come on. I know it's Friday morning. I know it's been a long week. But if there's a box on my doorstep, before I pick it up, what am I going to do so I don't hurt myself? Who's going to kick it? Somebody did say kick it. Somebody's going to kick it. And if I kick it and there's nothing in it, what's going to happen? If it's just an empty cardboard box and I kick it, what's going to happen?
It's gonna move forward a little bit.
It's going to move. Now, if now we put some mass in there, we'll put the calculator in there, I'm going to apply the same kick, what happened? It didn't move as much. Didn't move as much. So now if I put a second calculator in there, apply the same kick, doesn't move as much. But I applied the same kick in each time. And that application of that kick is a force. We've applied a force to the box. And the reason that we want to do that is because one of the things that we now know is the motion of this box is going to be relative, or it's going to be dependent upon the mass associated with the box. So the kick is a force, and we know those forces because we call them interesting things. Somebody said a push. A push is a type of force, and so the Newton's laws for physics defines a force as a push, or what's another way I can get my box to move? A pull. So I can either do a push or a pull, and that is fundamentally a simple application of a force. A force is going to be a push or a pull that's going to hopefully generate some motion. Hopefully generate some motion. Doesn't necessarily, because right now my box is sitting on the floor and it's not doing nothing, right? It's just sitting there. But in order to get it to do something, I'm going to have to apply a push or a pull to get it to move. Or I could pull up from the floor with a lift. But right now that box isn't doing anything. But we know that my force, whatever force that I apply, the force that I apply is going to be proportional to the mass. So in order to get the same motion, if the mass is increased, I'm going to have to apply a bigger force. And this is something that Newton called inertia. And inertia is essentially a resistance to motion. So it's a property that's going to give this resistance to motion. inertia is that idea that, and it's actually not a resistance to motion, it's a resistance to a change in motion. So we're going to get this idea of resistance. So I'm going to use my handy dandy box here. This is actually turning out to be a good, see, love physics because physics can do fun things here. All right, so I got my handy dandy box. I have my calculator on here. I'm going to zoom out. Okay. Now, if I pushed on the box, I haven't done this test, so we're going to change here. All right, so I got this on the edge of the box. So if I push on the box with a slow and steady force, not a whole lot happens. We just get a slow and steady force and we get an interesting thing that crosses the video, right? We just get something totally interesting that crosses the video and we're going, okay, that's important. All right? All right. As I mentioned, you're going to get at least a couple of bar tricks out of this class. Those of you who went to lab yesterday got bar trick number 1. You're about to get bar trick number 2. For those of you who haven't been to lab, this is bar trick number 1. All right. Now, so I'm going to pull on the box slow and steady. And again, we got nothing more, and my calculator just going to sit there. All right. Now I'm going to pull on the box. Or just do that. Now, fundamentally, the only thing that happened in my calculator, it didn't go this way very much. It just flopped down. Because it has inertia, it has a resistance to motion. Now, so let's think about what's happening here. Now, we've got another force that's acting with us right now, especially when I'm doing this.
Is the resistance from everything else?
Well, it's a resistance from everything else, but let's think about it. Let's think about it from a perspective, and I'll show you a different one. So we're going to do a different one here. All right. So my calculator's sitting on my box, and I'm going to rotate my box. Okay, I'm going to rotate the box this way. I'm going to rotate the box, rotate the box, rotate the box. Calculator's not doing nothing. Calculator's not doing nothing. I get higher, and then all of a sudden it slides off. So the question is, what's holding the calculator on the box at this point? Because it should slide off, right? Well, now it did slide off. But my calculator, even at this point, it would slide off. If this were ice, when's my calculator going to slide off? A lot sooner than when it does when it's on the cardboard. I didn't even change different cardboard. This is a really slick cardboard. That's nice slick cardboard. This is a little rougher cardboard, so I can do the same thing with this cardboard. I'm going to lift up my calculator, and it's going to slide off at a different angle. So what's holding the calculator onto the cardboard? Friction. So we've got friction that's causing us to do that, and that's actually what's going to happen here. And we're actually going to end up working a problem with this a little later, is that what's holding the calculator on the box, at least initially, is that the acceleration that I'm providing to the box doesn't overcome the force due to friction. Now, when I apply a higher acceleration, I overcome that force due to friction, and the the calculator just falls straight down. Because the calculator has inertia. Everybody drives a car, right? And we put our soda or our purse or our backpack or our glasses or something on the car seat beside us, and we're driving along and we go, oops, the truck is stopping. stopping at the railroad tracks and we slam on the brakes, what happens to the stuff in the car seat?
Goes forward.
It's going to slide forward. Because inertia, again, has this idea of this resistance to a change in motion. So what's happening with the stuff that's in the car, it's traveling down the highway just like you are at a certain velocity, and all of a sudden I slam on the brakes, and unless there's something there, like your seatbelt, it's going to keep on going. It's just going to totally keep on going. Totally keep on going. We see it happening. It's just going to totally keep on going. And we've seen it on the space station, right? Or the space station. They send the pin across the space station, and it goes out there and it floats around until the other person gets it. Or in the Sandra Bullock movie, which I've never actually seen, only seen the pictures of, you know, somebody gets cast off and they start floating away in space until what happens? Until it's acted upon by another force. That force could be a wall. That force could be the other astronaut catching it. That force could be something that's going on there. So we get Newton's first law of motion. But he actually makes three postulates here. And the first one is an object in motion or at rest remains in motion or at rest unless acted upon by another force. So my object's going to remain in motion, or it's going to remain at rest unless acted upon by another force. And so what's happening with our box situation is that once I apply a force that's greater than my force due to friction, my calculator's going to fall straight to the ground. Now, if I'm only applying a force that's less than that force due to friction, the calculator's going to come along for the ride. And we've probably all experienced this sitting on the tailgate of a pick-em-up truck. If somebody guns it, we're usually going to go plop into the mud puddle at the back of the pick-em-up truck. We've all experienced that. This is the tablecloth trick, by the way. This is the tablecloth trick, by the way. This is what happens here. So we get our first law of motion that an object at rest remains, or an object at rest remains at rest, or an object in motion remains in motion unless acted upon by a force. So let's think about forces for a second, because motion is going to come about. So I've got a situation here. We got this person pulling with a force, and this person is pulling with a force. And if these forces are equal, what's going to happen to my flag?
Nothing.
Absolutely nothing. Now, this person applies twice the force. What happens to my force? Or what happens to my flag?
Moves to that guy.
It's going to move this way. So if I do twice the force, we know that the flag is going to go that way. So an interesting thing that we've just deduced. We know something about forces. If it has direction, it's going to be a vector. Okay? So force is a vector. Because it's got direction. And we know we can add or subtract them. Because now I'm going to ask you, how much is the force on this particular flag going to be?
You're gonna multiply it.
Well, if this is twice the force this way, and this is pulling one force that way, this is actually going to be moving this direction with a force that has a magnitude of just one of them. And we know that. I mean, because if we did this, I got a hockey puck. It could be an air hockey puck. It could be an actual hockey puck. And I've got somebody that applies a force with the stick there. And we got the other person that's trying to take the puck away, and they apply with the force here. We have a pretty good idea of which way the hockey puck's going to go. Any guesses? Folks on the line, any guesses? Which direction is the hockey puck going to go?
Are the forces equal?
Huh?
Are the forces equal?
Yeah, the forces are equal.
Diagonal.
Northeast.
Yep, yep. Hockey puck's going to go off that direction. Because I can add vectors, I can add my force vectors just like I can add my velocity vectors. Just like I could add my acceleration. So I can add my forces, so we gotta really take into account. So if I write this is force A and this is force B. So force A, let's write it in vector notation here. So force A is going to have the magnitude of the force in the I direction. And remember that if I'm writing this out on something, that just by putting the I as a bold, that's telling you it's in the I direction. And I've got force B, that's giving me a force in the J direction. I can add those together, and my resulting force, which usually uses a little r, is going to be force I plus force J. And so the ultimate magnitude of that force, remember, is that this is going to be the square root of F squared plus F squared, which is going to be, it's going to be F times the square root of 2. And we know that the tangent of the angle is going to be my y component over my x component. And so I'm going to end up with the tangent of 1. And it's going to ultimately tell me that that's a 45-degree angle. So we're going to be able to add our vectors and add our forces just like we've done with our vectors, which is why I spent so much time on vectors. But this also starts talking about that my net force is going to be from the sum, and we're going to use this symbol to mean sum. It's going to be the sum of the forces. So we usually refer to it like that. So we're going to add up our forces, and that's going to give me the net motion of whatever my object is. So let's go back to our box here, because this is a special force. This is a special force. We give this one a special name. We call it the normal force. And you'll see it represented with a little n, and you'll see it represented with a capital N, depending on the situation. And that is the normal force. It's the force that's resulting from the push from the floor. or the push from the inclined plane, or the push from the wall, that we get this force that's in here, we get that push back. Now, we know gravity's acting on it, and we've talked about mass. And this is another key thing. Mass is not equal to weight. Mass and weight aren't the same thing. Although we've done a really good job of confusing them. Because if I weigh something in chemistry class, I'm weighing it in kilograms and grams, and I'm telling you that's the mass. It is. But if I'm in the English system and I weigh something, I'm telling you it's pounds. But pounds aren't the unit of mass in the English system. Anybody know what the unit of mass in the English system is? I think we even talked about it way a while ago. So those of you online, what is the unit of mass in the English system? Anybody in here know?
Is it PSI?
PSI is pounds per square inch. I'm really not expecting you to know, because we don't use them very often. But you gotta kind of know it. It's a slug. The unit of mass in the English system is called a slug. Pounds are a force. Weight is a force. Mass is that resistance to motion. Weight is a force. And in our systems, whether that's going to be the mass times my acceleration due to gravity. That's going to be my weight. So weight is a force. So if I'm doing, in the English system, a pound is defined as a slug foot per second squared. A newton, which is going to be our unit of force, is going to be a kilogram meter per second squared. And this again is a derived unit. So a newton, which is what we're going to end up working with, they're going to be kilograms meters per second squared. Weights are going to be mass times the acceleration due to gravity. So we're going to get our weight, this is our mass times the acceleration due to gravity. And we're going to talk about this normal force, which is a lot of times why we use the small n. But we also use a big N, which gets a little confusing when we're using N for newtons. But typically we use the big N only when we're doing force due to friction, which we'll show you in a little bit. But we're going to get that part of it. Okay. I think I have just enough time to do Newton's second law. So we start talking about that our motion is going to be a result of the sum of our forces. And we already know that in order to get motion, my force has to be proportional to my mass. And I'm going to do this a little bit differently. than the way the book does it. So we started with the box, right? And we applied a kick to it. And that kick could be described as an impulse. And that's a force over a duration of time. So really we can define an impulse as the force times its change in time. And you guys actually had a problem. Remember we had the problem where we had the ball hit the wall and we told you how long it interacted with the ball and then it came off? And we looked at that motion, that homework problem, and we talked about the change in velocity. And we actually used that information to calculate the acceleration that happened. So that homework problem really works for us because we say that this impulse that happens here is related to what we're going to call a change in momentum. And yes, I know we don't see momentum until a little bit later, but I hate just giving you Newton's second law the way we always see it without understanding what Newton was saying. Newton said that the second law related to the impulse was a change in momentum. So we're gonna apply a force, and we know this happens because let's look at what's going here. I can do a swift kick and get this to really move, or I can do a slow kick and get it to move much slower. I could be applying the same force, but the change in time is making a big difference. So this idea of impulse and a change in momentum really is important. So if I do this, and I'm going to define momentum. So I've got my force is, and momentum is defined as mass times velocity. It's defined as mass times velocity. So if I do this change in momentum, I get my force is a change in time over change in momentum. Now, there's a weird math trick that allows me to do this change here. So let's use this weird math trick. So I can do the change in mass times velocity, and this is actually the mass times my change in velocity. So it's a strange math trick. But let's think about this for a second in most conditions. I can have a change in velocity of my calculator as I'm pushing it down, right? But while I'm doing this, is anything happening to the mass of my calculator? Am I doing anything to the mass of my calculator?
No.
No. Most of the time, we don't have a change in mass. Now, there are situations where I have a change in mass. Rockets. So most of the time, I get that the force times the change in time is equal to the mass times my change in velocity. Now I'm going to divide both sides by change in time, and I get the force is equal to the mass, change in velocity over the change in time. And that looks like something we know what it is. What's the change in velocity over the change in time?
Acceleration.
Acceleration. And this is the common form of Newton's second law. what we normally say is the sum of my forces, or my force net, is going to equal mass times acceleration. And that's what we're going to use an awful lot over the next several class periods. And we'll ultimately come back to this idea about the change in momentum. But I like talking about the fact that Newton really talks about the second law as in terms of impulse and momentum, which gives us this form of the second law, which we can use a lot, but it's not the whole story. It's not the whole story. Because this isn't always the case. It does a lot for us, but it's not always the case. And I'm going to stop there because I don't want to confuse things more. Questions from anybody? All right, make sure you guys get the test in by tonight. And we'll go from there.